Hello, good morning, good afternoon, good evening, everyone, wherever you might be. It is my great pleasure to welcome EVGENIOS KAKARIADIS from Newcastle, and he will tell us about Morita equivalence for operator assistance. EVGENIOS, the floor is yours. Take it away.
Thank you very much, Piotr, and thank you very much for the invitation to give a talk in this amazing seminar. I've been following it for the past year, on and off, and it's like it has been great. So I hope I'm not like I hope I rise to the expectations. Also, disclaimer: I know that it's being recorded and this will stay forever. So forgive me for any innocent mistakes that I may make. I know that I won't be able to go back in time and fix them. Right. So this joint work with George Lefterakis and Ivan Todorov, and it's about operator systems and notion of Morita equivalence. And let me start with the motivation of this idea. Well, something that we all know and like. So the main idea is to, or the philosophical definition of Morita equivalence in my head is to examine an object via actions on modules rather than in itself. And this idea is behind many settings, like when you study groups or rings, or even with system algebras, you study the representations on by actions on Hilbert space. So in this sense, Morita equivalence means equivalent representation theories. Somehow, even though I'm still waving my hands here, I'm just trying to give what I feel like it should be. Or another way to say it is to compare objects up to matricial representations, in the sense that a ring R is Morita equivalent to the n by n matrices with entities from R. Another way that I like to see this, I like to see Morita equivalence is by inducing mutually matricial approximate identities, in the sense that you have a setting that allows you to pass from R to matrices on S by completely positive maps, and from these matrices back to R, and this diagram commutes when you take a limit. So you have a setting that allows you to do that in some sense for R and S, and that idea that is one of the main tools that is being used in this theory. Right. I will open the chat also just in case there are questions, so I will keep in mind. I'll keep in mind also here. Right. There are equivalent ways for seeing Morita equivalence in ring theory. So you can say that they are Morita equivalent if and only if they have equivalent. The categories of left modules are equivalent. So you have two functors that, up to some natural transformation, they give you the identity. That's one way of seeing it. Another way of seeing it is through the composition. So you say that R and S are Morita equivalent if you can decompose R as a balanced product of n by n and S of n by R by m. And this isomorphism is as you see R as a bimodule of itself. Another way is to see it through balanced module maps. So you may have M and N that are bimodules, and you have balanced module maps that are compatible from M times N to R, and respectively from N times M to S. And another way of seeing it is through some kind of stable isomorphism. That means that the representations, when you take the countable sum of R and the representations of that are the same with the representations of S. Morita equivalence makes sense for especially in the non-commutative context, because the commutative context is just isomorphism. Right. And then things get more interesting in the operator space theory, starting with the work of Riffel for sister algebras. There you can have a notion of Morita equivalence that now has some things that are common and some things that are slightly different. So for sister algebras A and B, we say that they are Morita equivalent if and only if you can find what's called an primitivity by module M over A and B, so that M star M gives you B and M star gives you A. I'm somehow implicitly posing that I see everything in a common B of H here. But if you like, you can use the Hilbert space, the Hilbert module theory in order to make precise what M star M and M star means.
And what do you mean by these square brackets here?
So the square brackets, when you see them concretely, I mean the closed linear span.
Okay. Cool.
That line is a little bit of a white lie, but it is made more precise by the second one. So you can see, so you can realize Morita equivalence by putting A and B as corners in a common system algebra C, so that these corners are full, meaning that whenever you have an ideal of C containing A, it has to be C, and the same thing for B. The categories of left operator modules are equivalent. That's something Bletcher showed a couple of years, well, several years ago, and so that passes here as well. And also you can see Morita equivalence as the composition by using by modules, well, by using sister correspondences in these languages, M and N. In fact, you can choose N to be the dual of M in the set, the M star. Another equivalent way is again through balanced module maps. And in the special case, when you have A and B to be sigma unital, you can realize Morita equivalence through stable isomorphism. And here K is the compact operators on L2. Okay, and I will be referring to this A, okay, the minimal tensor product as the stabilization of A and respectively the stabilization of B. And again, Morita equivalence in this setting extends isomorphism for commutative sister algebras. In fact, you can show that Morita equivalence gives you isomorphic centers. Right. In this class of sister algebras, there are two ways, at least, that to somehow you can take two routes then to pass to other objects in operator space theory. And this has been main idea in the past years, or these two main ideas in the past years, for extending the notion of Morita equivalence to operator algebras or operator spaces. And the first pathway that you can take is to take as a definition this decomposition of the algebras into some kind of tensor product. And instead of using a tensor product, stabilized tensor product, you can use the high group tensor product. That can be taken as a definition, and it has been introduced by Bletcher, Bewley, and Paulsen for operator algebras, and has been studied in several works later by Bletcher, Kashyap, and other people. And it has been very fruitful. It recovers, first of all, most of the results of in the C-star theory, most of the Morita results in the C-star theory. One thing that doesn't recover is the stable isomorphism, though. So in the presence of a unit, you may have Morita equivalent operator algebras that are not stable isomorphic in this sense. Okay. The idea behind this is that it's based on that an evolution, or if you're talking about operator space, and a multiplication is not available. So somehow you live inside the category, and you try to make sense of Morita equivalence inside the category of operator algebras by trying to avoid to use any type of evolution. So that's one pathway. The other pathway is to actually try to use some kind of evolution. So you may see when you write the decomposition of A and B by using an impermittivity bimodule, and if you use a concrete realization, you may see them as in this sense, like that M star AM gives you B, and MB M star gives you A. So in some sense, this is a kind of unitary equivalence. If you see the symbol M, the impermittivity bimodule, as being what a unitary represents for operators, the impermittivity bimodules represent it for system correspondences. So use that and extend it up to faithful representations in order to have some kind of an abstract notion of Morita equivalence. That pathway was introduced by Eleftherakis and was started by Eleftherakis, Paulsen, Todorov, and other people, including myself. And it recovers most of the C-star Morita results, and also it recovers the stable isomorphs. And it's stronger in the sense that if you have Morita equivalence in this sense, then it implies Morita equivalence in the sense of Pletzer, Muley, and Paulsen. And here the aim is to use the involution when you represent the objects in sub B of H. Alex, you're about to ask a question.
Yes. Hi, EVGENIOS.
Hello, how are you doing?
Good. So like, I wanted to ask you, like, what do you mean exactly by concrete realization? Like M star A, M inside B, and do you assume M to be an impermittivity bimodule or just the C-star correspondence?
And I'm assuming that it's an impermittivity bimodule. Okay, so and you may see it inside the linking algebra.
Okay, so just the usual tensor product, like
or you can see it as a tensor product. That would be the same. So instead of having multiplication here, I could have the stabilized tensor product.
So what is the difference then from for like this as opposed to what was before? Like
no, that's
A is sorry. Yeah.
That's the same. If A and B are C-star algebras, that's the same. These two things are the same for C-star algebras. The point is that then you choose, well, you take one of them. Okay, you take one of these equivalent pictures of Morita equivalence, and you made it make sense in a more general context, in that of non-self-adjoint operator algebras.
So
and you try to see where you can do. Yeah.
So do you replace then A by operator systems or operator A modules? Or
that will come. Yes, that is about to come. Yeah.
Okay.
Yeah.
Thanks.
So I should say that one of the first steps, like with Blessing, Muley, and Paulsen, and with Eleftherakis, was to do it for non-self-adjoint operator algebras, and also check the weak star versions of these objects. Okay, so dual operator algebras. And I think that was mentioned in some talk about Morita equivalence. I'm going to change the terminology, and instead of impermittivity bimodules, I will talk about TROs. And the reason I'm going to do that is because I'm going to move beyond having a C-star algebra A and B star. I'm not going to start with C-star algebra A and B. I'm going to start with a closed-up space M that satisfies that M star M is inside M. Okay, so if this is concrete, then you can see that M star M produces algebra and gives a nice product taking values in M star M, and that makes it a Hilbert-Wright module, and it becomes Hilbert-Wright module. So I'm going to refer to that as a ternary ring of operators, a TRO. Okay. And again, you can, well, either you can see it as a unitary or as a partial isometry, right? If you want to have an analog of what the symbols mean, should mean for single operators. Okay. Before I pass to the work with George and Van, I want to set a little bit of notation and also say some things about previous work that I had with George about on operator spaces. So a concrete operator space will be a non-closed subspace of B of H1, H2. And will be called unital if H1 is a H2 and X contains the unit. And the morphisms here are going to be completely contractive maps. I'm going to say that the map is non-degenerate if it is non-degenerate with respect to X and the adjoint, right? So that's a little bit stronger from just having that phi X K1 generates K2. I also want the dual of that, the phi X star K2 generates K1. And again, the bracket here is the closed linear span. It's not hard to see that whenever you start with a map phi, then you can define the spaces, the subspaces, and you can take the compression there. And in all the entries outside the compression, you have zeros. So you basically up to norm or up to not adding zeros, then you can assume that the maps are non-degenerate. Another notion that I'm going to use is that of the injective envelope. So a unital operator space admits the smallest sister algebra it can generate inside its injective envelope when you endow the injective envelope with its OEM infrastructure. And that's called the sister envelope. In the non-unital case, you can have a similar construction, but instead of having a sister algebra, you have the smallest TRO that it generates, and that's the TRO envelope. And the way that you construct the non-unital case is by using Polster system. I will give the picture of a Polster system later, but what you do when you have X to be non-unital is that you take 2x2 matrices where you put X in the 1, 2 entry and then X star, and then you fill the other two with complex numbers. And that's a nice unital operator space. It has an injective envelope, and in there you construct the TRO. Right. In all definitions I'm going to give, there are two levels. One level is the level for concrete objects, for realizing concretely the Morita relation. And the other one is the abstract level where you define the same relation up to representations. So to start with, we say that two operator spaces X and Y are TRO equivalent. We're using also the adverb strongly, but we have dropped it now. So they are called TRO equivalent if you can find TROs M1 and M2, so that X can be written as M2Y M1 star, and Y can be written as M2 star X M1, and everything is represented concretely so that all these multiplications are compatible. Once you have it, automatically you have an extra structure on your operator spaces. So your operator spaces become operator by modules with respect to the sister algebra generated by M2 M2 star and M1 M1 star for X and the dual for Y. So that extra structure always appears in the TRO equivalence, and it's helpful and it's there, and you cannot close your eyes and forget it. And we say that two operator spaces are delta equivalent if they admit completely isometric maps with TRO equivalent ranges. So if they are TRO equivalent up to some representation. Okay. It is not hard to show that TRO equivalence is an equivalence relation. You play with some tricks by, well, for transitivity, you play with some tricks in order to construct a nice TRO, passing from X from the first one to the third one. But in order to show that they are delta equivalent, you need to do a little bit more. And that's perhaps the point of the next slide, which is what have been the main tool that we had used in that work with George. So if you have TRO equivalent operator spaces X and Y, then what you can do is you can start inducing representations from one bimodule to the other. So if you start with a non-degenerate representation of the X as a bimodule, then by using the usual trick as you do with Morita equivalence, by constructing M1 star tensor the Hilbert space and M2 star tensor the Hilbert space, then you can induce a not-general representation on Y. Okay. In the same way that you would do it for sister algebras. Nothing changes, and you basically use the fact that you have a TRO. In fact, in this way, you can induce also representations of M1 and M2. And in that way, from TRO equivalent X and Y, you can pass to TRO equivalent to TRO equivalent phi X and psi Y. Piotr, you have
yes. Thank you for noticing. So you have this pi phi sigma. You know, I don't know to say that it looks Greek to me. There is such a saying. It looks Greek to me.
Okay.
But if you would elaborate, these are maps from where to where. I know that it's a representation of this bimodule, but I'm a little bit confused. It goes from which space into which space. So pi phi sigma are maps from where to where.
So so phi is a representation of X. So it would be a complete locative map on B of H1, H2.
Okay.
Okay. And sigma is a star representation of M1, M1 star on B of H1. Okay. And pi on H2. And I'm so happy that I put H1 and H2 in the right order and I didn't mix it.
Yes.
But that's what it means. So you have a triple a bimodule. You have a bimodule representation.
Yeah, but it actually makes perfect sense. You have bimodules, you have left algebra, bimodule, right algebra. So these three maps, okay?
Yes.
And of course, they go to Hilbert spaces such that it makes sense.
Yes.
Okay.
Yes.
Yeah, thank you so much.
And then by applying this trick, like you take M1 star H1 and sigma acts is from M1 star M1 star on B of H1, it gives you another Hilbert space. And applying twice, you get the original one up to a unitary equivalence. Okay. So in that way, what you deduce is TRO equivalent images. So when you start with two TRO equivalent spaces, what you can conveniently or canonically do is you can fix one representation of one operator space to be completely isometric, and then build another completely isometric representation for the other operator space Y, so that they are TRO equivalent. So in some sense, you have a control, at least for the universe of one operator space, and you can construct the other. In particular, you can take X to sit inside its injective envelope, and this is helpful for showing that delta equivalence is an equivalence relation. So if you have X, Y, and Z, what you would do is you would take if you had Y, X, and Z to be consistent with what I've written here, you would fix the representation of X inside the injective envelope. You have an induced representation of Y, an induced representation of Z, and these representations would be TRO equivalent to the same representation of X. And because TRO equivalence is an equivalence relation, that would give you that Y and Z have representations that are TRO equivalent, and therefore you get transitivity in this way. That's why it requires a little bit more work to get the delta equivalence relation. So that's one trick. Oops. And the other trick is that if you are in a situation where your sister algebras coming from the TROs admit good approximate identities, in the sense that you have sequences that produce these approximate identities by taking more and more partial sums, rather than having a net of finite combinations, then what you can do is you can pass from X to matrices over Y by augmenting them by using the elements from M2 that you require, and then you can pass from MKY down to X by killing by multiplying with rows and columns. Okay, and that what will give you is a sequence of maps that in the pointwise norm, it will go to the identity on X. And this is this help for approximation arguments, and that's the link with before. Yeah, Piotr.
Just to double check, the C, not CIA, CAI, this means central approximate identity, right?
Contractive approximate
Contractive, sorry.
Contractive approximate identity. Yes, yes, yes. Right. Some results that we have from that work. First of all, with the first trick, TR equivalent spaces admit equivalent bimodal representation theory, but I'm not claiming the converse of that. Actually, the converse would be a very nice thing to have. I don't have a clue how to get it. As I said, strong delta equivalency relation, and stable isomorphism implies strong delta equivalence by standard tricks that we would do for sister algebras. Conversely, if you are in the situation where your spaces are separable, or that you have some sigma unital conditions on the sister algebras related to the TROs, or if the spaces are unital, then strong delta equivalence is stable isomorphism, which is good to have. In general, strong delta equivalent operator spaces have strong delta equivalent TRO envelopes. And if you're in a unital situation, then you get stable isomorphic sister envelopes because you have, well, unital sister envelopes. That's why. If two operator algebras with contractive approximate identities are strong delta equivalent, then as operator spaces, then they are also Morita equivalent in the previous theories of Bletcher-Muley-Paulsen, and also in the sense of Eleftherakis. And if well, and in this way, strong delta equivalence is indeed Morita equivalence for sister algebra. So it's an extension if you want. And another thing is that when you pass the second duals, then you get what is the strong delta equivalence in the sense of the Eleftherakis, Paulsen, Todorov, which is the weak star version of these results. I should say this, that there are two, that again, two pathways, like one for the norm closed objects and the other one for the dual, for the objects that in the weak star theory. Alex.
Yes. So can you explain again, like, what is the difference really between TRO and delta equivalence? And also, like, I'm still struggling to understand what is the meaning behind delta equivalence. Maybe like where does the delta?
I will. Yeah. Well, I was hoping not having that question because I don't. Okay, the delta comes from the original work of George, and I'm afraid I haven't really interrogated him on this. So TRO would mean relations concretely. So you have X and Y concretely represented, and you have the relations. Let me get. And you have these relations happening there with well, with the product making sense. Okay. Yes. And delta equivalent would be that X and Y have some completely isometric image in some spaces, and their images are TRO equivalent.
Okay, and then that can be different, like also for C-star algebras, or no, for C-star algebras, I guess.
So for C-star algebras, like with this tool for C-star algebras, for a faithful representation of a C-star algebra, you will find a faithful representation for the other one that are concretely Morita equivalent, meaning that meaning that this would happen: M star times A times M equals B. Sorry, M star times the image of A times M inside the image of B. Okay.
It can be different, like for C-star algebras, even like being TRO equivalent versus delta equivalent. If X and Y are already like known to be C-star algebras, but basically forgotten.
If they are TRO equivalent, then they are then they are delta equivalent through the identity representation. Okay. What you want to do is you want to then remove the existence of specific representations for your objects. Otherwise, you wouldn't have a passage between, or you wouldn't have a theory that gives you equivalent representations. That's the only thing that happens with delta equivalence. Like you abstract and you say that up to a representation they are TRO equivalent. That's what you say.
So, like delta equivalence says that there exists a representation, like a completely isometric, where they are TRO equivalent.
Yeah.
Do you also have a notion of being like TRO equivalent, which does not refer to that they are already like represented in some ambient space like B of H1, H2?
Yes, that will come for operator systems. Okay.
Okay. Okay.
I'm not sure if this will answer your question, but there is indeed something that does refer to representations. Okay. Okay. And you will stop me again there. I'm sorry. We're happy to answer. All right. Good. So that's yes.
If I may, I just
Luca,
would like a confirmation after the answer to Alex. So the TRO equivalence is for already represented systems, and the delta equivalence is that there exists a representation such that they are TRO equivalent.
Exactly.
Okay, thank you very much.
So that has been happening for operator spaces, and we were our motivation then was the work of George for operator algebras. So we said, okay, can we do it for operator spaces? And something that we totally missed is something in between, like something between the operator system, a class of objects in operator space theory that is very important. So for this, perhaps an operator system. A concrete operator system will be a closed self-adjoint subspace of some B of H. And the morphs here are unital completely positive maps. Okay, the isomorphs are completely ordinary paddings in the sense that unital completely positive have a unital completely positive map, a UCP from now on that has an inverse that is also a UCP. And there is an abstract characterization of operator systems. So if you start with an S that has an involution, it's a vector space with an involution, and suppose that you have a cone fixed inside every matricial and matricial level of S, and you want them to be to come from Hermitian elements. You want this cone not to intersect the minuses, and also you want them to be compatible with multiplication with matrices with entries from scalars. Okay, in this logical way. You also assume that you have what's called an order unit and which becomes an Archimedean unit. I'm not going to go through the definition, but in the sense, if you weren't concretely represented, that would play the role of the unit of B of H. Okay. And if these things happen, then you can find a complete order isomorphism from your star vector space with this data to a concrete operator system. Okay, that sends also the Archimedean unit to the unit of H. And the way to do it is you just take what you can take, like you take the unital completely positive maps of S inside in MN, and then you add them up in a sense, and you show that this is the complete order isomorphism that you want. The reason that I'm putting it here is because the abstract definition or the abstract characterization of an operator system is very useful when it comes to constructions that have like tensor products or direct limits or co-products. It's a very nice way to show that you obtain new operator systems from older ones. Great. I wasn't sure if I should include this, but someone can ask, okay, why do you care about operator systems? Since algebras are already okay, operator spaces are the other extreme. So why something in between? And well, there are a couple of points for motivation. First one comes from Steinberg theorem that completely positive maps are exactly compressions of star homomorphism. So operator systems arise through the range of compressions of star homomorphism quite automatically. I say that, well, sorry. Also, I commented about the Paulsen system. So whenever you have an operator space that may not have a unit, then you create the Paulsen system and you pass to the unital now operator spaces where things tend to work a little bit better or a little bit easier. I'm saying that one reason for using operator system is to encoding missing information. Well, they do find application of quantum information theory, but also another nice application comes from positive definite completion problems. So you may have a partially complete or complete matrix, and you ask if it can be completed in a desired subclass of positive definite matrices, and operator systems play a role there. Another, yeah.
What do you mean by saying that the completely positive maps are the analog of a positive measure? I always thought that this notion is related to the notion of this state space, not completely positive maps.
Yes, you got me there.
Just the states, like how do you say, like the completely positive maps into complex numbers are just the states, and these are the positive measures.
That would not be enough to have to have the structure that you would like. You also want complete positive maps inside of taking values in a man in the matrix algebra. So that so not just having scalars in the range, but also having n by n matrices. For example, I didn't want to go there, but okay, there's also a notion of non-unital operator systems, and the way that you construct them would be to use completely positive maps, taking values in n by n matrices.
EVGENIOS, could one say that these completely positive maps are analogs of positive measures up to Morita equivalence?
Yes. Yes, because well, for Morita equivalence, you pass to the matricial levels.
Exactly.
Yes.
Yes. Okay, so that's very conceptual.
Yeah.
Okay. And I have a stupid question since we are at it. What's the difference between the usual C-star envelope and injective envelope?
The C-star envelope is generated by the space inside the injective envelope, assuming unitality. Okay, so an operator space has an injective envelope. The injective envelope becomes a C-star algebra with the Choi infrastructure, it has a natural way. There is a natural way of making it a C-star algebra. And the C-star envelope is the C-star algebra that you get from X inside the injective envelope that's generated there. It may not be. It may not be the same. The injective envelopes are by default larger than the C-star envelopes. So the way that you would make the injective envelope you endorse C-star algebraic structure would be like you have. You see it inside the B of H, and you take the projection from B of H inside the injective envelope because of the injective envelope property. And then when you multiply two elements inside the injective envelope, you multiply them in the original B of H, and you take the projection inside the injective envelope. But the main difference between injective and C-star envelope is that the C-star envelope is generated as a C-star algebra by X.
Okay, thank you.
And another thing that I will try to comment at the, well, I hope I will have the time to comment on, would be that for undirected graphs. So undirected graphs can give us operator systems. But for this work, we were, for Morita equivalence for operator systems, we were motivated by the work of Kohn and Van Salcombe. I hope I said that right. Where they used operator systems related tolerance relations. So thank you, Walter, for that, for the thumbs up. So whenever you have relations that are equivalence relations, you would form groupoids, but in their work, you assume only reflexivity and reflexive and symmetric, and therefore you get operator systems. So you break the notion of multiplication. And also they have a nice sequel paper on that, and Walter has given a great talk on these things. So our motivation was to say a little bit more things about Morita equivalence for operator systems. So I'm passing now to what we've done with George and Ivan. Again, there are going to be two levels multiplied by two. Okay, so bear with me. So two concrete operator systems S and T are called TRO equivalent if you can find a non-degenerated TRO M, so that you can write S as M star TM and T as MS M star. Again, the way I see this is some kind of a unitary equivalence between S and T by a non-degenerate TRO. And I want non-degenerate TRO so that I have compatibility of the units. Like my operator systems come with units, and I do need to account for that. In practice, we can see that if we apply the unit of T or the unit of S, M star M will contain the unit of S and of T, respectively. And therefore, again, we have a bimodal structure on TNS that we cannot do without. And closely related to that is something less, okay? So we say that two concrete operator systems are concretely bihomomorphically equivalent. If you can do something similar, you have similar relations, but you drop the TRO, you just have an operator space X, and you just assume that X and X star are non-degenerate, so that they contain the unit. Okay. So this is something less, and it's good to have something less because it's less things to check. And in this case, what happens, well, of course, TRO equivalence implies bihomorphic equivalence, but also it goes the other way round by choosing, starting with such an operator space X, you just augment it to a TRO given by X times the system algebra generated by X star X. Again, everything is concretely represented here, so all these multiplications make sense. Okay, and taking evolutions, etc. Right. On the other hand, the second level, delta equivalence, is TRO equivalence up to representation. Up to representations here are completely, sorry, up to unital complete order embeddings. So S and T have some nice representation of B of H and B of K, in B of H and B of K, with TRO equivalent images. Okay, and same thing for bihomorphic equivalence. Again, if you have unital complete order embeddings, that satisfy this rule. And we denote this with these two arrows between S and T, and there is a reason for that that comes from information in the work of Stalke that I will try to comment on at the end. And the main theorem that we have is that delta equivalence for operator systems is the same with delta equivalence as operator spaces, and that's the same with stable isomorphism between the, well, isomorphism between the stabilizations in any sort. Okay. Right. In order to compare, I said before that the concrete versions of delta equivalence and bihomorphic equivalence are the same. In order to compare their abstract versions, I have to go a little bit deeper in the theory and have an abstract characterization of these notions that hopefully will answer Alex's question. Again, what comes with this setting is a bimodule structure. So inside the injective envelope of S, I can define the sister algebra of the multipliers of S. So it's the elements so that normalize S. So AS is inside S and A star S is inside S. And I will always write iota envelope to be the embedding of S inside the injective envelope, and therefore inject the sister envelope of that. And the unitality condition yields that this multiplier algebra sits inside S because I can simply apply with a unit here and I get something in S. So there's something that I cannot do without, but that's good. That's very helpful. In fact, I can transform delta whenever I have a delta equivalence between operator systems by using this tool for fixing representations, and then for fixing one representation and then using on the other one. I can make it so that the TRO can be chosen to give Morita equivalence between the sister algebras of the multiplier algebras of S and T, and also that the sister envelopes are Morita equivalent. Okay. This follows from the operator spaces results, and modulo that M1 and M2 are the same, and a little bit of tweaks here and there to account for in that you are working in a smaller class, that of operator systems. But the main point is that this delta equivalence can be realized in a nice way that gives also a connection between this data that come along with S and T. Okay, the abstract characterization of Morita equivalence requires that of requires the existence of trilinear maps, because I had things like M star S M. So I want to abstract this through trilinear maps. And so whenever you have ST and M, ST operator systems, M and non-generic TRO, a delta context will be when you also have two trilinear maps and they all satisfy a list of rules. M star M and M star are unital. S is a bimodule over M star M, and T is a bimodule over M star. These are things that come naturally. The trilinear maps are bimodule maps over these actions that have to be unital. And you have some compatibility relations. So you want some associativity between the trilinear maps. One comes from that if you apply the bracket trilinear map, and then you apply, well, that will land you in an S, and then you apply the parentheses trilinear map, then you can remove things in between, and because you have module actions, you can write them in this way. And of course, the dual. For whatever I say, I also have the dual of that. And a pre-context would be a context if, in addition, whenever I plug in the unit in the trilinear maps, I get the module action of M1, M2 star on the unit. And these are things that happen when you have TRO equivalence, right? The trilinear maps there will be just the multiplication rules, and all these things hold there. Right. We have a list of nice properties for delta context because of the compatibility relation. So if you apply 3 times, you get what you should get by removing parentheses and brackets. And the dual of that, because of positivity, whatever happens on the left-hand side happens also on the right-hand side, and the dual of that. And here is something good. If you apply the maps successively, but you apply with a unit, then you can start moving things around, okay, on one side and on the other side. Then again, if you were using multiplication rules, all these things would hold because of associativity of multiplication. Okay, and that's what these trilinear maps try to abstract. On the other hand, for the bihomomorphism context, again, you start with a pre-context. That means that you have ST operator systems and now an operator space that is non-degenerate. And the trilinear maps, what you ask from them is that they land you when you apply on the unit, but you choose X, whatever for X and X star, you land in the multiplier algebra of S and the dual for that. And we'll see why this is important. Again, you have the usual associativity relations, and in order to account for unitality for the TRO, here for the context, you assume existence of semi-units. Well, what these do is that there are columns so that the trilinear map on this element gives you back the identity to the limit. Again, if you have a non-degenerate operator space X and these trilinear maps are multiplications in some concrete environment, all these things happen automatically. Okay. Right. So the connection between all these items is that delta equivalence is the same with bihomorphism equivalence, which is the same as having the existence of delta context, which requires a lot of things, and the existence of bihomorphism context, which requires less things. And we have already seen why 1 and 2 are the same. And I also commented how a realization like at the delta equivalence gives you a delta context by multiplication, and the same thing for 2 implies 4.
Sorry, can you tell me
Yes.
one more time what number 2 means?
So number 2 means that they have SNT have unital complete order embeddings in some B of H and B of K, so that the relations with a non-degenerate X, a concrete operator space X, hold for their images. I can go back actually.
Okay.
A little bit. Yeah. So this thing with the arrows would mean that S and T have, say, phi and psi, complete order embeddings, so that phi S is X star psi T X, and psi T is X phi S X star. So you can realize this relation in some concrete environment. That's what it means.
Okay. And just a stupid question, why do you call the other guy delta equivalence? Why it's delta, not sigma or whatever? I'll give you the same answer I gave to Alex. Again, this has the root to the original work of George, and I wasn't that good of interrogating him. Oh, sorry, I forgot that you answered this.
No,
I'm so
it's
sorry.
fine. It's fine. No, it's fine because I will now will need to interrogate him.
Okay, now you have to.
Now I have to, like,
yeah.
This is twice in an hour. That's a lot. Right. So as I was saying, 1 and 2 are equivalent. 1 implies 3, 2 implies 4, because concrete realizations gives you the trilinear maps. So 3 implies 1 is the familiar trick as you would do for sister algebras by using this functor M tensor. And now one needs an extension of this trick to get 4 implies 2. But before I go to that, Alex.
Yes, so for if you have S and T already like C-star algebras, and say you forget that they're like algebraically closed, but only operator systems, and you know that, for example, there exists a delta context for sigma and for S and T for A and B, like then. So that's, I guess that's what you wrote before, like M star A M is contained inside B. That's like the completely bounded map, completely positive map, and the same way the other way around. Like if we know, like, does it imply already that the image is all of B, like M star A M is all of B, like in the same way, like, you know, like the Morita equivalent, I guess that's boils down to, which would give you that it's all of B. Is that?
Which would give you?
Like I mean, like that M star AM is not just contained in B, but it's actually like fills out B entirely.
If you have these two relations, both of them, then you can apply successively and you get the equalities. That you get it for free.
Okay.
Okay.
Yeah. Thanks a lot.
The only reason so in our paper we try to do it for possibly not closed self-adjoint unital self-adjoint subspace of B of H, where we have inclusions instead of equalities, but then when you pass to the closures, then you get equalities again because of some approximation.
Yes.
Because you pass the limits. Okay.
Yeah. Thanks.
Okay, so what is to show is that a bihomorphism context gives you a bihomorphism equivalence. So in order to do that, we will have to build complete ordered embeddings that realize the bihomorphism equivalence. So how you do that? Well, starting from S, you already have a representation that you like and you love inside the injective envelope. What you do next is you take the Hausdorff completion of X tensor H, the algebraic tensor product here, when it's endowed with a squilinear form where X1, H1, H2, H2, it is what it has to be. Like it is the only thing that you can do is you take X star and the identity in X1, and that's something in AS and therefore in S, and phi applied on that can be applied on H1 and H2.
Sorry, what does it mean? Hausdorff completion?
Hausdorff completion means that I take this squilinear form here. I take the kernel. I take the quotient by that kernel. Kernel, I mean the elements that give you applied give you 0, and that would be an inner product. And I take the completion of that quotient.
So this is called separation completion. Yes.
Oh, okay. I know it by the name Hausdorff completion, but that it can be the same. So ciscollinear form.
Name Hausdorff.
Ciscollinear form quotient out. You quotient out the kernel. You take the completion of that.
Sorry, I knew the name of Hausdorff, but not in this context.
Yeah. And you, sorry, Adam, you call it separation completion, right?
Yes.
Okay, thank you.
That's how I knew this construction.
Okay.
Then you take a kernel and then complete.
Okay, note. Okay, so we have a Hilbert space, and now what I want to do is I want representation of my X in B of H, comma K. K is the new space, right? And again, the only thing I can do is just concatenate by the tensor product. I'm not writing the kernel here, but it's implicitly it's implicit there. And the good thing with that theta is that the way that it kills the first factor of the tensor product is the logical one, right? Now it takes a little bit more work to induce a representation of T in B of K. And the way that you do it is by defining psi T on X1 tensor H1 and then the product of X2 H2 to be the only thing that you can do. Like the only thing that you can do with this piece of data is to take X star because, well, you want to move the adjoint here, and then have T and X1. That is an element in S, and therefore phi of that element can be applied on a vector of H. You do some work, and then the existence of semi-units and the fact that phi is completely isometric gives that psi is completely isometric. But I'm not saying that theta is completely isometric. Okay. But what happens is that theta of X is a non-degenerate space, operator space. And then if you write down your definitions, what you see is that theta psi2 star psi t theta psi1 is exactly phi of that, and that's the way that you get the bihomorphism equivalence back. If you apply this twice, like you start with phi, you construct theta, and then you construct psi, and then you start from psi and you construct a theta prime and a phi prime, then the phi prime is unitary equivalent to phi, and the theta prime is differed from theta by applying a unitary on one side, the same unitary. So applying twice gives you a Hilbert space that is unitary equivalent to H, and that helps showing the dual relation. And that's the proof. Good. I'm going to go a little bit faster now. So after we did that, we asked, okay,
you have half an hour left.
Okay, yeah, but I realized that I'm only halfway through.
And you're halfway through, yes.
So one natural question that comes out of any equivalence relation that you build is, okay, what kind of invariance does it have? What kind of things does it remember? And that is the motivation for the second part of the work. So first we started with the class of the UCP maps of S that, remember, S contains the multiplier algebra, so these UCP maps restrict to star homomorphism here. In some sense, these UCP maps defined by module maps on S over AS. Okay, and also we take the kernel of S with respect to AS to be the set of the subspaces that can be realized as kernels of these UCP maps. And the same trick with this, I really like this trick by taking the M tensor when M is a TRO, M tensor Hilbert space. This gives you functors from one side to the other side, and gives you so the delta equivalence gives an equivalence for this class of representations, and the morphisms for this class are like taking one representation to directly on the other. Okay. Also, the lattices, you can use a lattice structure on the kernel spaces, and they are isomorphic in the same sense that you would show that the strong Morita equivalence algebras have the same ideal lattices. Another thing that we have in the non-self adjoint theory is some kind of specific representations that are called maximum. So it can happen that a complete ordered embedding of an operator system has a dilation that is non-trivial. So the first representation sits as a non-trivial corner of something larger. Okay, and one can ask, okay, can you move? How far up can you move? The answer is that you can find a maximal dilation. You can find dilation as a maximal representation. And the second good thing is that the image of this maximal representation is going to generate the C-star envelope. So that has been the vision of Arveson for the C-star envelope and maximal dilations. It appears that delta equivalents preserve maximal representations, and in particular, they also preserve the subclass of Choquet representations, which are representations that give non-degenerate representations of the system. And also, it preserves hyperrigidity, which means that representations of S are somehow, well, have unique, completely positive extensions that are star homomorphism. I'm not saying it quite right. I'm hiding something here. But to give you an example, so what would be for operator algebras, the self-adjoint operator algebra of the graph would be hyperrigid if the graph is finite. So hyperrigidity is a nice property that's preserved by delta equivalence. You can ask the same question about another class of representations where the morphisms now are intertwiners, and again the answer is practically the same. Like you play the same trick, and it follows through. What was also a point of motivation is what happens with tensor products of operator systems. So Morita equivalence plays well with nuclearity and exactness. And we asked, okay, can we have something similar for operator systems? And it appears that these properties, in the same way that you have a tensor product characterization, equivalent characterization of nuclearity and a direct limit characterization of exactness, there is something similar also for tensor products here. This goes back to the work of Kavruk, Todorov, Olsen, and Tom Ford. And I will spend a couple of slides trying to set the ground and the main definitions, and then I will try to show you at least one proof for these results. So, in order to construct tensor products, you need two operator systems. Okay, each one comes with a cone structure and an Archimedean unit. You take their algebraic tensor product, and now you want to use an operator system structure on that. So you want to take a family of cones, and you choose these cones so that they satisfy some axioms, correct? The choice of these cones may not be unique, so you may have different cones, but still satisfying the same set of axioms. But are these axioms? Well, each cone has to be at the level, at the nth matricial level. They define an operator system structure on the algebraic tensor product, and the closure of that with respect to the induced norm will be, or the completion with respect to the norm will be denoted by S tensor tau, where tau is the name of the collection of the cones. You want some compatibility relations, so Pn tensor Qm lands you in CNM. And also, well, if you have a map from S to Mn and psi from T to Mn, then you can put them together and you get a new map with respect to the tau tensor product in the M of n times M, in the n times M matrices. Sorry, n times M square matrices. Now, as I said, you may have different structures, and it may happen that one is smaller than the other. So if the structure tau 1 is smaller than tau 2, we write that it's bigger, and this means that we can induce a map from tau 1 from the tensor tau 1 to the tensor tau 2. Okay, and the way that this can happen is if this positivity is weaker. And all the tensor products that I'm going to talk about are functorial in the sense that if I have maps from S1 to S2 and T1 to T2, then I can take the tensor product of these two maps and get from the tau tensor of S1 S2 to the tau tensor of S2 T2. It's not known if all of the tensor products I'm going to show you are associative. But being associative means that the natural thing that the tensor product respects the associativity from the level of the algebraic tensor product. Okay. But again, it's not clear whether all of them are associative. So I'm going to give you 5 of them. The maximal tensor product, which is going to be the biggest one, is characterized by the property that it linearizes every jointly completely positive bilinear map from S times R into an operator system to a complete positive map. And jointly complete positive here means that I can take whatever matricial structure I want here, MNS, and the same thing on R, MMR, and then I produce a new map on that takes all possible combinations between the entries from MNS and MMM R. And starting, and if you have such a map, then it lifts, well, it is, sorry, it induces a map on the maximal tensor product. The minimal tensor product is the one that you would expect, that you take two concrete representations and you take the tensor product of the Hilbert spaces and the operator system generated there. Okay. That's going to be minimal. The commuting tensor product, which is what we do, what happens in system algebras, is given. So the cone structure here is given the following way. An element in here is going to be positive if and only if its image under phi times psi is positive, where phi is a representation of S and psi is a representation of R in the same Hilbert space. They are both completely positive, and now we come to having commuting ranges. Okay. So far, well, for the maximal tensor product, I wasn't saying anything about commuting ranges. Okay. There is the essential left tensor product, where what you do is you take the closure of the algebraic tensor product of S by R inside the maximal tensor product of the injective envelope of S by R. So you see this already embedded here. And the essential right, you do the similar thing, but instead of having the injective envelope of the first factor, you have it on the second. Why these 5 things are important? Some properties. For system algebras, the maximal operator system tensor product coincides with the operator system when you have the inclusion of A tensor B inside the system max of A by B. So we're doing okay for system algebras. That's good. The commuting one is a little bit more mysterious. So if you have an operator system and you take the commute tensor product with the system algebra, then it's the same thing as taking the maximal tensor product. Also, you can see it as the structure induced by the inclusion of S tensor T inside the maximal tensor product of the maximal system algebra of S by the maximal system algebra of T. What we mean by maximal system algebra of an operator system, we mean that whenever I have a UCP map from S in a B of H, it lifts to a star homomorphism of the system max S inside B of H. And you can play a similar trick, like the commute tensor product can be also realized in the commute tensor product of one factor with the system max of the other one. Okay. What is brilliant and what they have shown in the work for authors is that the maximal one is the maximal one and dominates the commuting, which dominates the essential left and the essential right, and all of them dominate the minimum. So you have this hierarchy of tensor products that works very well. Now,
wait, and here the comma means that there is no relation between ER and EL.
Yes.
Okay.
Yes. So these are not somehow not comparable. Also, that's the point I should say that the commute tensor product, we don't know if it's associative. Okay, right. The notion of nuclearity that we like and we love from system algebras passes here, but we say that S is nuclear with respect to 2 tensor product structures if for any other operator system R we have a completely ordered embedding of the tau tensor product with the tau prime tensor product. Okay, and if these two are comparable, then you already have one map. What you want to show is that this map has a UCP inverse. Okay, and we say that it's nuclear if it is min-max nuclear, and of course the nuclear system algebras are nuclear as operator systems. So MN is min-max nuclear.
And can you go a step further and also define the nuclear dimension of operator systems?
That's a very good question. I don't know.
Okay.
I don't know. I know what that be. So you would, I guess the first point would be to abstract the dimension for function systems and then start from there. Yeah, I don't know. I don't know. Alex, you said that there is a typo for R equals T. So do you mean the definition?
I meant like before you had like a S tensor T and then changed it like to S tensor R. I guess that was just like
yeah. Okay. Sorry.
like
Yeah. That would be yeah. Sorry. Okay. I'll go a little bit super fast through because there's not enough time. So being mean L nuclear means exactness in the same sense that you would have for system algebras in order to have the sort of exact sequence when you take the spatial tensor product. Okay, so for every system algebra A, you have A tensor S by I tensor S with I being an ideal, and you have a map inside the quotient tensor S, and you want that to be a complete geometric isomorphism.
Wait, but this is just right exactness. How about left exactness?
Left exactness, I don't know.
Okay.
Mean air nuclear means the local lifting property for operator systems. So suppose that you have A and I ideals, and you have a map from S to the quotient. You choose E to be a five-dimensional operator subsystem in S, and you take the restriction of that, and you can lift it to a UCP map that on A that makes this diagram commute. L max nuclear means that it has the weak expectation property. That means that whenever I see S in the double dual, there is a canonical inclusion by UCP map, then I can extend it to the injective envelope of S inside the double dual. Okay, so this is fixed. It will take values still in there. And double commutant extension property is the same thing, but when you have a complete embedding from S to B of H, then you can lift it from the injective envelope to the double commutant of iota S. So somehow these properties, well, you can extend UCP maps by representation extension theorem, but the point is that you have a control on the image, and that's what makes a difference. Right, and the theorem, well, I'm saying all this stuff in order to say that all these properties are invariants of delta equivalence for operator systems. And the way that we do it is, of course, to check what happens with the tensor products. So the main theorem is the following. If I have delta equivalent operator systems, and I have a pair of factorial tensor products, so that one is less than the other, so I already have maps from going one way, then nuclearity for S with respect to these two tensor products pass to nuclearity of T with respect to these tensor products in the cases that characterize the properties in the previous slides. That is, whenever I have associative tensor products, or one of them is associative and the other one is the left essential or the right essential, or the other way around. And one more bit, whenever this pair is this specific L commutative. And we don't know if this is captured by the previous ones, because we don't know if the commutative tensor product is associative. The point here is the proof that I like. So to make a correction to the very first slide, whenever I have a Morita equivalence, I have some kind of matricial approximate identities. Okay, so T and S are delta equivalent, therefore I have such a diagram that in the limit will be commutative, okay, and phi and psi n are completely positive maps. The whole point is to show that for any R operator system, I get an isomorphism between MNS tau prime R to MNS tensor tau R. If I manage to do that, then I will get what I want for T tensor R. Why is that? because T tensor tau prime R, by applying phi n tensor identity, will land me in here. Then I have the map that I would like to get, and from that I apply then the psi n to get to the under tensor product by T. And if you follow the definition of these maps, because you have identity of the second factor of the tensor product, then the limit would be the identity, and that would be the UCP inverse of that goes from here from tau to tau prime. So the whole thing is to manage to show this, right? So the whole thing is to manage to show the following lemma, that whenever I'm in that situation, and S is tau prime tau nuclear, then MNS is tau prime tau nuclear. That's the whole thing that you need to show. I'm going to try this, even though probably I will miss a couple of things at the end. So I'm going to show you one case. I want to show you the second case, how you get from the point that S is tau prime L nuclear and tau prime is associative to the matricial level. Okay, so in order to do that, I will have to share my camera. Yeah, good. I hope you can see it. I'll go line by line. So I'm in this situation. I have this isomorphism, and I want to get the same thing for MNS. Correct. So what is important is the following. I have MNS tensor E L R, and I have M and S tau prime R. And let me also write here I MNS T no maximum. All right. So I know that I can induce sorry, that should be the other way. So I know that I can use a UCP map here, okay, and that's the map I want to have as complete ordered embedding. And I know by one of the properties of EL that I can see this inside here. So that's a nice embedding. So what I need to show is that I have an embedding from this operator system into that operator system, right? And so we start from one side. I'm writing MNS in this form. Well, you can use first the spatial tensor product, but again, MN is nuclear, so you can apply tau prime. You can use then, you can move the brackets because tau prime is associative. And you can again remove tau prime because MN is nuclear. And now, you know nuclearity for at the level of S. So you can pass to another isomorphism by replacing it, and by using the injectivity of the spatial tensor product, you can see this inside here. Okay, I wrote max again. Mn is nuclear, so if I write or if I don't write, it's the same thing. But if I'm writing max, I have max here and I have max here. So again, I can move brackets. I can use associativity of the maximal tensor product and have max here or not. Okay, putting them together, that's Mn of the injective envelope, and it has the property that Mn and the injective envelope operation they commute, and that's how you pass from embedding from here into here. So that would be also an embedding. That's an embedding, and therefore that is the required. Well, that's also a complete order embedding because of the way that they are defined, and that's the idea. And you play the same trick also in all other cases. What you try to do is you try to break MNS into here, and then somehow pass the brackets on the other side, and then move it back again. All right, let me go back to my slides. Yes, Alex.
So can you have different tensor products by matrices? Like for C star was okay, it's always the same one. But I'm like, if you take matrices, tensor, some operator system, like can they have different cones? Like
No, they're going to be. So that's what means. Mn is nuclear. So
okay.
And that's good. That's a good thing. That is used.
Okay. So you can always pick the tau prime, whatever you want.
Yeah.
Thanks.
Right. Hopefully a couple more things, a couple more cases. So we moved a little bit further to check specific operator systems like function systems. These are operator subsystems of commutative sister algebras, and our aim was to explicitly show that Morita equivalence or delta equivalence extends the notion of isomorphism from function systems, which would be a commutative setting. In order to define a center here, you have to be one has to be a little bit careful, because you have different representations of S generating probably non-isomorphic sister algebras. So for us, the center is realized inside the representation in the sister envelope. Okay, and that's the multiplication that we use to make sense of commutativity. And what we can show is that delta equivalence gives complete a complete order isomorphism between the centers. Therefore, if you have function systems, the sister envelopes are going to be commutative sister algebras. Actually, they're going to be the commutative sister algebras on the Sylow boundary, and their complete order embedding is just so delta equivalence for function systems is just completely ordered embedding. in a nice analog with what happens with sister algebras. On the other hand, rigid systems are on the other extreme. So rigid systems are operator systems where the multiplier is trivial, and there is an example that of Topic matrices from the work of Kohn and Seidelkomb. And in this case, what we get, if one of them is rigid and we have delta equivalence with T, that can happen if and only if T is isomorphic to some K by K matrices of S. Okay, so up to some level.
Sorry, can you remind me what is the superscript N in parentheses? S here.
Here, yes. Now, yeah. Now I'm having a mental block.
Sorry, I think that this notation is taken from this paper of Walter and Kohn.
It's so the operator system
is by the N projection of this. This is the operator system related to these functions on the circle when you truncate by a projection Pn, where Pn is the projection on the span of the first N, as far as I remember, basic vectors. Yes, am I right?
Yes. Well, this is exactly what the Toplitz picture shows here. Like you have an expansion and you truncate it at the nth level.
Mm-hmm.
It's a numerical matrix.
Yeah. So you are inside the scalar matrix.
Mm-hmm.
Okay. Thank you, Adam. Right. So in the case where, so the only way that you can get delta equivalence for rigid operator, when one of them is rigid, then it's just by going to a K level of matrices. And in fact, you can have the only way, well, the way that you can have it is even more stronger, but the multiplier algebra of T has to be K by K matrices. And I included the proof because it's a silly proof, if you want. So we said that the delta equivalence can be realized, so it gives Morita equivalence of the multiplier algebras. So you have a TRO which on one hand gives you as m star m the scalars, so it's a Hilbert space, and on the other hand mm star gives you a T which is unital, so it's a finite dimensional Hilbert space, that m, and that dimension is the dimension K that we want. Okay, and then you just use the similar tricks to expand them. Yeah, sure.
No, I'm just switching on to
Okay.
remind you that your time is over.
Okay, so in this case, I'm not going to say anything more.
I mean, you can wind it up. I mean, it's not like we have to stop right now, but just think about winding it up.
Okay.
Punchline, you know.
Yes. There is one more example of operator system coming from these directed graphs, these undirected graphs. And just to remind you, whenever you have an undirected graph, then you take the operator system to come from the matrix units related to the edges of that undirected graph.
Does it have any relationship to graph sister algebras?
No, because graph sister algebras you have directed.
I know, yes. But,
yes. So in this case, for you have undirected, and therefore you have also the adjoint of any matrix unit, and by definition it become an operator system. So between or you more generally you can have the D by D matrix. You can take an operator's subsystem of that. That's a non-commutative. That's called an NC graph. And I'm going to skip that, but what happens with this by homomorphism and the cohomorphism is that whenever the homomorphs with these objects are completely positive maps that come from a cross representation, and that's something that comes from the work of Stalke. And the notation was like from T you go to S by choosing a specific cross representation. By having a USP map with a Krauss representation.
Sorry, one more time. What is a non-commutative graph?
A non-commutative graph is a subsystem, a unital operator system of D by D matrices. So finite dimensional Hilbert spaces.
Mm-hmm.
In the finite dimensional Hilbert spaces world.
What do we call it a non-commutative graph?
Why you call it a non-commutative graph? The classical, well, because you have the notion of the classical graph.
Yes.
Which is going to be realized in the D by D matrices where D is the number of vertices. But this is not just this that doesn't give you all the operator systems that you can take. Right? You can take whatever non-self-adjoint. You can take whatever self-adjoint and unital subspace in there.
Okay.
So it appears that the notion of cohomomorphism is half of the delta equivalence in this setting, and that's why we had the two arrows. Like having one arrow gives you half of the relations for the bihomorphism equivalence. Alex asked how much different delta equivalence is with TRO equivalence. It appears that for non-commutative graphs, delta equivalence is realized at the level of the identity representations, because you are in the finite dimensional world and the sister algebras they generate are going to be automatically the sister envelopes. There are some technical lemmas there, but there is for classical graphs you can visualize these notions by pullbacks. So what's a pullback? A graph G is a pullback of H if you can have a map between the vertex sets, so that a connection in G happens if and only if you have a connection in the images. For example, if you take one vertex, okay, that means that it has a connection to itself, then a pullback of that is any complete graph on D vertices. complete graph, like you can have edges from between all of them. So TRO and delta equivalence here means that the graphs have are pullbacks of isomorphic graphs. And I think that is a good place to stop. So I will try my magic button and get at the end. So thank you. There were a couple of things I didn't say, but thank you very much for your attention.
Okay. Evcharisto para πολύ. Okay, so it's time for more questions. Maybe Mark, would you like to weigh in, since you are the father of Morita for sister algebras? Any comments, maybe starting from you?
No, this is all new. I hadn't followed any of this, so I'm just very interested to see how far it's developed, but no particular comments at the moment.
Okay, good. So now, guys, you can fire at will. I don't see any raised hands. Adam.
Maybe I would like to ask a question, very general. In fact, one feature of Morita equivalence is that if you have Morita equivalent algebras, many invariants of this algebra are the same.
Mm-hmm.
For example, K-theory and so on.
Mm-hmm.
And what can be said about this operator systems? Is there any topological in flavor, kind of a topological invariant for operator system, or there is none?
Adam, it's unfair. You stole my question.
Mm-hmm.
Sorry.
Yeah.
Piotr, still you can ask about differential geometric kind of invariants.
Yeah. Well, I don't have anything like, I don't have something that pops right now. How can you tell them apart?
And
right?
I'm asking this question because you see, I don't have a good intuition about this operator system. So since if you just take a look on the definition is very general. There is no kind of product in the structure, but somehow it behaves very much like sister algebras, which is very surprising. So.
Yes. Topological invariant. I don't have an answer to that, apart from the properties that are shown that are preserved by delta equivalence. It is indeed mysterious and or funny that they have like killing just the multiplication rule, but sitting inside B of H still gives you such a rich structure.
Yeah, but to follow on Adam's question, the way I'm thinking about it is that the invariants that you showed us for this Morita equivalence were kind of specific constructions. Maximal is preserved, something else is preserved, some particular things are preserved. But I was, when you look at these invariants like K-theory or cyclic homology, then these are functors. So maybe one could generalize Adam's questions to ask, what if you think about functors from the category of operator systems into some much simpler category, maybe not numerical, but like abelian groups, like it is for K-theory or cyclic homology. And then you can say, aha, so these functors are preserved by my Morita equivalence.
I think, I don't want to say because, but I suspect that whenever you use like the trick of tensoring with M in order to, as a functor, so M tensor is a functor gives you a functor between categories. When you have Morita equivalence of sister algebras, and that plays really well. So for representations, that plays really well and goes through but you may have seen, or you may have spotted that although have equivalent representations, we don't have enough to say for the converse. Like if what kind of equivalence between representations will give me back?
Okay, that's a nice point.
That's
yes,
and I mean, even for sister algebra, that's not Thomas.
Yeah, Thomas, go ahead.
You are muted. Sorry.
I'm trying to. Oh
Yeah,
yes, it works.
You're unmuted.
Yeah. So I have a comment to the last problem. It has an obvious solution. For instance, we know that the Morita equivalence of operator systems induces Morita equivalence of sister envelopes.
Mm-hmm.
So every invariant of the sister envelope is a Morita invariant of the operator system.
Okay.
So, but it's a cheap solution to the problem.
Yeah, but it's a good point.
Yeah. I have 3 questions. So first, I don't know if it's related to function systems.
Mm-hmm.
All they are about this comparison between sister algebras and operator systems. So first of all, is there a class of operator systems known for which Morita equivalence is an isomorphism?
Sorry.
An analog of commutative sister algebras.
So the function systems play well with that.
Mm-hmm.
So the function systems are so Morita equivalence. Let's call it Morita equivalence for function systems is complete order embedding.
Mm-hmm.
I don't have. Yeah, but we don't have like I can give you more classes where this class of operator systems this class for operator systems Morita equivalence is complete order embedding, if I understood the question right. So we checked like we checked a couple of examples and we have on one hand the function systems, which is one extreme, and on the other extreme the rigid systems, and they give you different pictures. We are in the process of understanding what it means to be delta equivalent when you fix one of them to live in a class. Like, but perhaps I shouldn't say more because it's something in progress.
Well, Tomek, I understood your question in the following way: that is it true that if you have 2 function systems that are Morita equivalent as operator systems, then they are isomorphic, right? Was it your question?
Yes, in particular, yes.
That's a yes.
Okay,
yeah.
Great. So,
but my question was about the biggest class,
yes,
maybe beyond function systems, restricted to which the Morita equivalence is an isomorphism. It would be an analog of commutative sister algebras. So they could be, let's say, commutative operator systems.
Yes.
Yeah.
In quotation marks.
Yes.
Okay. The second question is: are there known conditions on Morita equivalence of sister envelopes sufficient to recover Morita equivalence of operator systems?
To go the other way. No, there aren't.
No. In one direction, there is no condition. Every Morita equivalence of operator systems uses and Morita equivalence of sister algebras envelopes. Yes. So my question is opposite, in opposite direction. If you know that sister envelopes are Morita equivalent in the usual sense, and you know that these are sister envelopes, what is needed to say that it comes from Morita equivalence of operator systems? Is there some abstract characterization of such sister algebraic equivalences?
No, I'm not aware of we were not aware of any. and that would have to somehow account for the fact that you would need the Morita equivalence at the system to be somehow canonical, because if you let it loose, then like you can have isomorphic sister algebras that for you can have isomorphic sister envelopes of operator systems, and the operator system may have no relation at all, may look completely different. Yeah, so I don't know how one would, I don't have an answer, and I don't know how one would go in the other direction for that.
I see.
So Tomek, so your question was kind of like you would like to move from flatness to faithful flatness, right? You know, only preserve in one direction, but you can also go back. Yeah. Okay, any other questions?
Yes, I have a third question.
Oh my goodness.
The third question is about also the relation between sister algebras and operator system. So having an operator system, we have a category of representations of it. Okay, and if you speak about envelopes in mathematics, all envelopes have the following property, that representations of your system which is enveloped correspond to representations of this enveloping algebra. It's like enveloping algebra for Lie algebra and other examples.
Okay.
So this is the usual meaning of enveloping.
Of enveloping. Okay.
Yes. So I wonder if it is so for this sister envelope of the operator system. What's the relation between representations of X and Hilbert modules of this sister envelope of an operator system?
Can you repeat the last part?
What's the relation between the category representations of a given operator system and the category of Hilbert modules of the sister envelope of this operator system?
That would be a good step, trying to figure out the converse.
Well, first of all, so there are two obvious questions. Is there a functor? And second question, can the image of this functor be characterized?
Yeah. So as you said, you may have you may have class of representations. For the sister, so there is the sister envelope and there is the enveloping sister algebra. These are somehow two different things. The enveloping sister algebra is the maximal thing that you can create, and the sister envelope is the minimal thing that you can create, and is related to maximal representations, even though not all representations of the sister envelope are maximal. Okay, so there are some technicalities there. Having such an answer would so what we tried was to understand what would be the natural class of representations for the operator system, perhaps in relation to the enveloping sister algebra or perhaps in relation to the sister envelope, that would allow us to go to build a functor and having a functor between these representations, equivalence, equivalent functor, go back to delta equivalence. But this is something that we couldn't see. We tried to pass through the sister algebra theory to do that, but it seemed it was not enough, and we got very restricting results, the ones that we tried. So so for operator algebras, one would go to operator modules and act on them and look at this category. But for operator systems, we're not sure yet. You gave me the the three questions that are like we have gaps.
Okay. Maybe one quick question
Yeah.
to check if I understand the notion of a sister envelope.
Yeah.
Is the sister envelope defined by a universal property?
It's defined by co-universal property.
Co-universal.
So first of all, I realized I'm looking here. So because it's the sister algebra generated inside the injective envelope, it's the smallest sister algebra that it generates. This means that if you have, let me write it. I'm going to continue share. Okay. So why is it like that? So the sister envelope of S, for some reason it lags. I will describe it. Okay.
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 So the sister envelope of an operator system has the following two properties. First, it is generated by a unital completely ordered embedding of S. Okay, so it's a sister cover. And secondly, for any other unital complete ordered embedding of S, generating some sister algebra C, you can find an epimorphism from C inside the sister envelope of S. That's why I'm saying it's a co-universal property. It's at the bottom of the. It receives arrows, and of course this is done in a way that it preserves the elements of S in a natural way, right? So the embedding of S in both C and the sister envelope is preserved by this star epimorphism. On the other hand, the sister max of S is the biggest sister algebra. So for any unital complete positive map from S inside of B of H, you can extend it to a star homomorphism of the sister max of S inside B of H. And the way that you would construct the sister max of S, it would be to take S, to build levels of S by taking an algebraic tensor product with itself and construct something huge. The way that you would get the sister envelope would be to go inside the injective envelope and build it in there. So two different.
Okay, thank you very much.
As an example, if I may, so if you have a function system AK, the maximal sister algebra would be the continuous function on K. The sister envelope would be the sister algebra on the Syloff boundary of K. So the smallest subspace of K when you take the restriction map on the operator system, still you have an isometric homomorphism, an isometric map.
Okay. Thank you.
I don't see any other volunteers. Oh, Alex, go ahead.
Yes, very quickly. So I'm trying to get my head wrapped around some examples of Morita equivalent operator systems. So what I have in mind is for C-star algebras, for self-adjoint operator algebras, I would just say something like, I take a hereditary subalgebra and I take its ideal, and I know that this defines my Morita equivalence. Do you have some canonical examples for operator systems in this vein?
So that would go through a linking algebra, right? And we don't have a linking algebra construction here. Perhaps in connection with Thomas' question, perhaps one could ask for a linking operator system that would sit canonically inside a linking algebra of coming from the sister envelopes. So that may give you that may give you a pathway in both directions. How that would be.
Do you maybe have some examples in terms of I don't know, I have some operator subsystem, some operator system in some in some usual operator algebra, like, I don't know, like some graph algebra, some conspiracy algebra, something like this. And then another subsystem where I know that these are, where you know that these are more
yes.
equivalent.
So I went a little bit fast through that, but I won't bring it up again. So for the undirected graphs, you have the operator, take two undirected graphs, construct the operator systems of them. Then there will be Morita equivalent if and only if the graphs have isomorphic pullbacks. So that's a very specific case where you give a geometric equivalent characterization of delta equivalence.
Yes, I see.
And there it's very well. The role of being finite, of being in a finite dimensional space plays a fundamental role.
Yes, yes. Yeah,
can you explain again, please, what a pullback means?
So the pull, I will try. So the pullback means G is a pullback of H.
We are talking graphs now,
undirected graphs.
Undirected
yes.
graphs.
Undirected graphs. If you have a map between the vertex sets from G to H, and you have a relation between two vertices in G, if and only if the images are related in H. As an example, if you take the single vertex, okay. A single vertex is related to itself. That's given. That is in the definition. So any complete graph on D vertices will be a pullback for this vertex, because you can trivially have the map from all vertices to one, and two vertices in the complete graph are related even only if their images are related. So that that's the pullbacks of a single vertex.
Okay, so if I did correctly, I have two undirected graphs, and I say that one undirected graph is a pullback of the other one. If it is, for starters, a complete graph, so every two.
You don't need to have a complete graph. The complete graph comes from this specific example to have a single vertex. But
okay. So it's not a complete graph, but it is a graph. And if two elements, two vertices are related in this graph, then after being mapped to the other set of vertices in the other graph, they also must be related.
Yes.
Okay. Indeed. But then it's like a pullback, right? Because it's you can have many of such pullbacks. Okay.
Yes.
Okay. I'm happy now. Thank you. Alex, you want to continue your interrogation?
I think that's a nice example. Like it matches like with this things that people work on, like with confusability graphs, right? Like where you have like you have some graph and you can send it to some other graph, and if you can confuse vertices, like for example, like if you send some vertices to a single one, you can't distinguish them anymore, right? Like that fits into this picture, like that people are talking in quantum info, like
that's
so
yes, that's exactly the precise words, because what Morita equivalence, well, it does distinguish between R and M and R, right? So yes. That's why you get this pullback in delta equivalence for these specific operator systems.
Yes.
They're not distinguished anymore.
It also matches with this, like if you think about, for example, Morita equivalence for directed graphs, where you like construct them like usually by saying like you construct, like if you have two different vertex sets and you have like edges between, you construct edges between them, they would like define like some sort of Morita equivalence, right? Like just here you have like another yeah, I think I get it. Like it's a good, I think it's a very nice example.
Okay.
Thanks.
Thank you, Alex.
Okay, anybody else? Now I really don't see any volunteers, so let's thank EVGENIOS again. Thank you so much. This was,
thank you for the hospitality and for the excellent questions.
It's our pleasure. So I'll stop recording now.